Welcome, ladies and gentlemen. My name is Łukasz Głaszczuk, and I represent Poland. I'd be happy to present to you our solution to task number 16, magnetic cannon. In this task, we are to consider a line of steel balls that are stuck by a strong magnet. Now, this system is placed in non-magnetic channel, and another ball is projected towards the system. Due to collisions, energy is transferred, and the last ball is ejected at the surprisingly high speed. We are to optimize the position of the magnet for the greatest effect and determine the maximal velocity independence on relevant parameters. So first, let's introduce some important terms in this problem. As a strong magnet, we will understand the neodymium magnet. We use plastic channel in order to prevent any additional magnetic interactions, and we will define the magnet's position by the number of magnets before the magnet A and number of magnets after the magnet B. Here you can see the phenomena presentation. Ball is propelled slowly towards, it accelerates, collides with the magnet, and the last ball is ejected at a very high speed. So why does this happen? We will try to explain this in the simplest way possible. If we have a ball that is propelled towards the magnet, its final position is is closer to the magnet than the initial position of the ball ejected from the magnet. Therefore, the potential energy loss is greater than the potential energy gain. And we can write the balanced energy equation, including energy loss, gain, energy losses, for the difference in kinetic energy. We are to maximize this value. Therefore, we think that we should minimize the number of balls before the magnet, maximize the number of balls after the magnet, and the total number of balls should be small in order to minimize the energy losses. Therefore, we conclude that the parameters A should be 0 and B should reach some optimal value. So in this problem, we distinguish between three different phases. First, the attraction phase, then a collision phase when the energy is transferred through the system, and at the end, the ejection phase when some of the energy is stored in the last ball and it ejects at the high speed. I will start our theoretical model with explanation of the attraction phase. For this, as all the dissipative forces are very small in comparison to magnetic forces, we decided to use conservation law to describe this phase. We use the equation for conservation of momentum and the equation for conservation of energy. However, in those equations, there's one parameter that is still not known. This is the potential energy loss, and the question is how we could determine this value. We decided to do this because it turns out not to be an easy problem, because the balls are ferromagnetic. Therefore, they're magnetized in the magnetic field. They create their own magnetic field that can influence the system. Moreover, if we look at the magnetization curve, it is a hysteresis, so it's hard to model this using a simple theoretical model. Therefore, we decided to investigate the potential energy gain in experimental matter, and this value would be supplied to our theoretical model. For that, we used a following system. We had magnet, plastic rings, and a steel ball. We detached the ball from the magnet, and we measured the maximum force. For that, we used the electric balance that we deassembled and used for our advantage. Here's the tensometer that we used to measure the force. Here you can see some results. You can see that the force is very high near the magnet, and it decreases rapidly with the distance from the magnet. Using this data, we can interpolate it, and then we can calculate the area under it in order to find the work done by find the potential energy change. We can see this also on this graph in a more condensed form. Each of these points represents energy gain, absolute energy gain for different situations, and we can see that the optimal energy gain is when there's no balls before the magnet and is slightly dependent on number of balls after the magnet. Having this, we already have this term. However, there's one more term that we should discuss further. This is rotational energy. If you look at this system, there are forces acting on a ball. This is magnetic force and the friction force. However, if we calculate the orders of magnitude of those forces, we can find that the magnetic force is much greater than the friction force, and therefore we think it can be neglected. Moreover, work done by this force here is very, very small, and we choose not to include this in theoretical model in order to make it simple. So rotational energy change is negligible. Therefore, we can just exclude this term and arrive with those equations. So this is our model for attraction phase. Now let's move to the collision phase in order to understand how the energy is transferred. And here I would like to stress that this is the part where the energy is not conserved, and we will calculate the dissipation of energy in the system. So let's take a look how this collision looks like. At first we have a ball, it collides, and the last ball is ejected. This is our first thought, and we thought that this would be a way to describe the system. However, it turns out that if there are many balls after the magnet, this situation looks much much more different. More than one ball is separated from the system. Therefore, the simplified theory is not enough to describe what happens in the system. There's energy dispersion in the system. All the collisions happen at once, and therefore more balls can be ejected at the very end. In order to describe this in a theoretical manner, we had to introduce some theoretical theory of contact theory. We use the Hertz contact theorem, which describes the elastic force acting on two balls when they are deformed. And we also can add to this equation dissipative force, which will be responsible for this dissipation of energy during the collisions. The rho parameter is determined from material constant and geometry of the system, and the rho parameter has to be determined empirically. We did it in a separate experiment. Having these equations, which are non-linear equations, we need to do some simulations in order to actually find what happens during the collisions and how the energy is transferred. So we can look closer at this graph. We can see that this is the velocity of the first ball, second, third, fourth, and fifth. All of those balls were initially at rest, and this had some initial velocity. What we can see here, that there's not the energy is distributed between balls. It is not like last ball has all the energy is distributed. However, if we add dissipation to the system, things get more interesting. What we see is that there's loss in energy. The total energy at the very end is about 24% smaller than the initial energy in the system. And this is the source of energy dissipation and most limiting factor in our problem. So now, as we know about the collision phase, we can move to the ejection phase. Here, again, we use the conservation laws to determine this means the conservation of momentum and conservation of energy in order to determine the final energy of the ball. Again, we have this parameter of the potential energy gain, which we found experimentally, as I've shown before. So now, we have to conclude our theory. For the attraction phase, we use conservation laws to describe the system. For the collision phase, which is where the energy is not conserved, we use the Hertz contact theory and provide numerical simulations to determine the behavior of the balls. And at the end, we have ejection phase when we again use the conservation laws. So this way, we can predict the ejection velocity in our system. In order to check if our theory is sufficient and enough to describe the system, we made some experiments. So we had a table when we could accelerate the ball. We had a system which we investigated. This, in our experiment, it looked, the size of the balls was 1 centimeters, and here are the masses of the elements in our setup. And this system looked like this. We had a photo gate, which allowed us to measure the time between by measuring the time between two photo gates, we are able to determine the velocity of the ejected or incoming ball. So here's our comparison between experiment and theory. So here there are no more fitted parameters. Here's our experimental data and theory. And as you can see, the theory we provided is sufficient to describe the system very well. However, we see some tendency here, which is very small at the beginning, is that the velocity is increased with impact velocity. So is there a limit to this effect? This is what we ask ourselves. So we extended our research for greater velocities, and we found following graph. So what is very interesting here is that at some point, mainly this point, on the right, the velocity, the ejected ball, is smaller than the impact velocity, and here the ejected ball has higher velocity than the impact ball. So this will be where we gain the energy, and here is where we lose energy, and the maximal energy that can be provided from a given system, velocity provided from the system, we define as this crossing here, and in our case, in our situation, was 2.3 meters per second. So now we also discussed that the position of the magnet is important, and there are other several important parameters that we should investigate. So let's first look at the position of the magnet in the sequence of the balls. We can see here on this graph, for initial velocity equal to 0, we chose this velocity as for this velocity we gain highest energy gain in comparison to the initial energy supplied to the system, and we can see that there is a maximum at when there are free balls after the magnet. Okay, so not everything. Okay, so to this point, we made experiments. We compared this with an analytical theory. However, not everything can be done in a simple laboratory. For some, in order to investigate some parameters, we had to use another tool, mainly the numerical simulations. We use a finite element method to calculate the field around the magnet in our system, and we were able to determine several values such as energy and force acting on a ball using the numerical simulations. From those simulations, we found out that the most optimal value for the setup is where the magnet has the same radius as the ball, and when its length is the same as its diameter. Therefore, we conclude that the cube magnets are better than the long ones or the wide ones. We also investigated how the scale of the system is important. You can see that when all the system is small, it may behave different when the whole system is large. And we found out that when we increase the scale of the system tends to have higher higher velocity of the ejected ball. However, it goes higher, but it may reach some limit or go into infinity. However, further points here would be lose its physical significance, as this system here is 16 centimeters in diameter, which is quite large, and I think it's enough to investigate it up to this point. So to sum up, we used conservation laws and contact theory to describe the behavior of the system. We provided the experimental data as well. We compared it with theoretical model, and we investigated crucial parameters for the system, as the position of the magnet, and for other parameters, we made some numerical simulations for those parameters which were not easy to obtain in experiments. So to conclude, energy gain is mainly from the magnetic interaction. Velocity of the ejected ball depends on initial velocity, number of balls in front and at the end of the magnet, dimension of the magnet, scale of the system. Best setup has no balls at the beginning of the magnet, 3 balls at the end. Maximal velocity, our setup is 1.3, and the best magnet has ratio of diameter to length equal to 1. Thank you.
Opponent, you now have 2 minutes for technical questions.
Thank you. I have one question. Could you open, please, slide number 23?
23, of course.
This is the theoretical figure, yeah?
Yes.
Thank you. How did you approximate the attraction force? By what kind of formula exactly?
Which attraction? What do you mean by attraction?
Magnetic, yeah.
Okay, so we did not approximate it in theoretical model. We made some experiments in order to provide us the actual data. We tried also deeper approximation. However, we found out that deeper approximation is not sufficient enough to describe this interaction. Therefore, we decided to stay to the experimental data as it is most reliable.
Yeah. You showed us the experimental data, and you said that you integrated the approximation formula. Could you open, please, this slide?
Yes, of course.
Yeah. What type of formula in mathematical meaning you approximated it?
Like this is just interpolation by straight lines between points.
Yeah, thank you.
No more questions. You have 2 minutes to prepare. 2 minutes.
Yes. Excuse me. At this moment, am I allowed to talk with the team? Yeah.
Thirty seconds. Ouais. Shh. You have 5 minutes. Ah, non, mets en pause. Attends. Ok. Thank you.
Good evening, ladies and gentlemen. My name is Sergey. I represent the Russian team, and now I'm glad to be the opponent. First of all, I have to thank the reporter for a good solution. In my opinion, it was exactly a good solution. The problem in the first view, very simply, but we have some interesting and difficult problem phenomenon which we can consider in the solution. So, according to the task, let's consider what happens in this problem. First of all, as I can, first of all, reporter told us about traction phase, collision phase, and ejection phase, and considered the energetic approach for considering these phases. In my opinion, it was it was good because energetic approach can be applied in this case. Its advantages. So then, but I would like to precise how reporter considered the traction phase because in my opinion we can consider not only slipping of the first ball but and rotation, and in the discussion I have to speak about rotation of the first ball and the second ball, how this part of kinetic energy of these balls can influence for our phenomenon, etc. Then, reporter considered the process of collision, and in my opinion, it's a great advantage that reporter applied the theory of Hertz of propagating the elastic influence through the chain of balls. It's advantages. Also, Also, reporter told us about their numerical simulation. In my opinion, it was also advantage. But thank you. Reporter told us about magnetic field in each balls. In each balls, but he considered this phenomenon only from the qualitative position, in my opinion, but didn't predict it in any one theory. Probably it's appropriate, and probably we'll discuss later. So, according to the task, we have the video when we have multi-stage setup, two-stage setup. I didn't hear this case from the report, and also I would like to ask the reporter why he didn't consider the multi-stage setup, two stages on three stages, and also according to the video from the
1 minute.
From the task, we have the fixed chain of ball. In my opinion, it's most simple case, but reporter considered the non-fixed chain, why it was done, and how the results change when we will consider the fixed chain. So, to sum up the report, I would like to say that that in my opinion this problem was solved, but I have no entire solution, because we can't hear the optimization of this experimental setup. We didn't have seen experimental setup. Thank you.
Now there is a 5-minute discussion between the reporter, the opponent, and the reporter and opponent. Sorry.
Okay, so I would like to firstly thank you for all your remarks and try to address all of them during the discussion. And firstly, let's talk about this multi-stage canon. As you
Yeah,
said,
of course,
important.
it's very interesting
I would
question.
just like to stress out that. Okay, I would just like to stress out that the task doesn't specify that we have to use multi-stage canon, but this is why. But the same question was asked actually during selective fights, so we decided to make yesterday some more measurements in order to provide some data that we can discuss on. Mainly, this graph represents what you are talking about. If you have a multi-stage canon, first, let's say initial velocity is 0. So the first canon would bring the ejecting velocity to 1.5. Okay, so we now have velocity of 1.5 supplied to the next canon. Okay, so we have 1.5, then we have about 1.9 from this. Okay, so we have 1.9 here, and there's a limiting velocity here. So if we investigate multi-stage canon, we can also investigate the physical properties of this system when we increase the impact velocity.
Yeah,
so it's like the same, we investigate the same thing in this manner.
Exactly.
You also asked about fixing of the magnet.
Fixed chain, yeah.
Yes, okay, so we tried experiments with different setups. We tried to use, for example, squeeze the magnet, fix the magnet, and we did several things, because you can always extend on the content of the problem. So I can show you just that, yes, I agree with the opponent that fixing a magnet may increase this effect.
Yeah, of course.
And
According
here's
to
a
the task,
photo from our experiments where we obtained the velocity of 3.2 meters per second when we fix the magnet. However, when we investigate the physics behind this, I would try to make this problem as simple as possible, make some boundaries, because we always add a coil to the system to increase the magnetic field. You can do many things, but in order for systematic approach, we decided to stick to all the things that we are supplied in the content of the problem and not add anything more.
okay, I have one question about how the impulse propagates through the chain. You showed us the experimental setup, how you measured the recovery factor with the pendulum, yeah? And did you investigate how energy propagates not from this one ball, from another ball, from the magnet, between the magnet and ball?
So you're asking, did we investigate how the energy is transferred between every single ball in the system?
Yeah.
Okay, so
between,
I think it's
between magnet and ball.
Okay, so
Is it different?
okay, so I agree with you that it may be a bit different. However, the scales of the system are similar, and the material properties of neodymium are similar to, I mean, the Young modulus, and this factor here is very similar to the magnets of the ball. Therefore, not to complicate our problem, we decided at first make an assumption that would be sufficient to describe a magnet similar to the balls, and basing on this assumption, we derived full theoretical model. We checked that this is actually applicable and agrees well with the experiment. Therefore, we concluded that this assumption was valid.
So let's turn to the physical meaning of the process. I would like to turn to the issue about rotation of balls.
Okay.
Please describe how what happens with the first ball and the ejection ball when the first ball approach near the magnet and the last ball ejects. When this ball rotates, when non-rotates, how did you describe it in your
so firstly,
model?
let's say that the
1 minute.
Okay, so firstly, we actually investigated the work done by friction during this process. So this work is is actually independent if the ball has some initial angular velocity or not, because the work would be the same, and and the condition for the slipping to occur would be the same. And what you're saying is that this ball can have rotation. However, the main the impulse that is transferred through the waves is not due to the rotation. It's mostly due to transversional velocity. Therefore, it is sufficient to just calculate the transversional velocity. And if you ask about the ejecting ball, it also has some big impulse at the beginning, has some high velocity. And before it rotates, we have to give it some time. Also, in our experience, we use photo gates. However, this was a very simple setup, and we ask ourselves if it is sufficient to use photo gates. Therefore, we use high-speed measurements to determine the velocity exactly, then we moved back to the simpler setup.
Now it's time for 2 minutes questions from the reviewer.
So, hello everyone. I will have some questions. First question for the opponent, please. You talked about a recovery factor, I mean, in your presentation. What do you mean by that, please?
Recovery factor. Can I slide? Can you show your slide?
Which slide?
With the pendulums.
Okay.
Yeah. Non-recovery factor. The part of energy which can transfer from one ball to another.
Okay, thank you. Now, a bit on the same topic for the reporter. You did hear a very good theory about spherical balls, but in your chain you have actually a squared magnet. Did you apply other coefficient for the contact between the square and the spherical?
Yes, we use the same coefficient, and I have a good motivation for that. Should I explain that?
No, I think we could discuss it further, maybe you and the opponent. I have another little technical question. You used some support for your chain. What was the matter? Is it plastic?
It's plastic.
It's
the
plastic.
coefficient of friction between balls and the plastic is 0.16.
Okay, thank you.
This is the only important parameter here. And it's not magnetic, of course. So it's
Okay, that's
30 seconds.
fine. Could you show us once again the graph with the forces, please?
for which force? Okay, magnetic forces. Okay.
Yes.
Yes.
Where is taken the origin of your distance?
Okay, it's distance between magnet and the ball. So it's the space between magnets and the ball.
Okay, thank you. That's all.
Thank
You have 1 minute to prepare. You have 2 minutes.
So, good morning, everyone. So, I'm Arsène from the team from France, and I'm gonna review this presentation about magnetic cannon. So, first, let's remind really clearly what is the problem in this question. So here you have the setup from the subject video, and the question where determine the maximum speed of the final ball you can have, depending on the position of the magnet and the other properties of the system. So now, let's see what are the different answers the two teams gave us. First, the answer of the reporter. The first point is that they treated the influence of the number of bolts before and after the magnet in order to answer the first question, with precise measurement and also outspeed measurement. They also have a great modeling of the magnetic field in this complex system and also accurate modeling of the soliton and the propagation in the chain of ball. Then they also measured the maximum speed in their setup and also had other study like a computer modeling for the size of the ball and the magnet and also a scale of the setup. So this is quite a complete answer of the problem. The opponent then pointed out some lack in this presentation. For instance, into the video, the magnets were fixed. So what is the influence of this fixation and it could maybe increase the speed. And also they pointed out the lack of experimental measurement and checks of the modeling.
1 minute.
So, about the discussion, the good point was that the opponent asked accurate questions and that there were a good repartition of speech time with the question and the answers, and there were really precise answers from the opponent. But maybe the discussion could be more interesting with a more deeper physical question and also treat more precise points. That's why I pointed out 3 different aspects of the problem that I think would be interesting to treat. First, the soliton propagation model. What are the parameters needed in order to modeling this propagation? How to check the efficiency of this propagation. Then about the magnetic field model, what are the parameters needed in order to compute it? And finally, the link between the magnetic field and the force. Is really the dipole approximation wrong? And what about the influence of the permeability?
Thank you. So now there's a 4 minutes discussion between the reporter, the opponent, and the reviewer.
First, I would like to address one of the physical topics you brought up during the review. Mainly, why do you think that the propagation of the wave is a soliton?
Yeah.
You say that it's a soliton. Soliton is a specific type of wave.
Yes.
And why do you think that when you have a dissipative medium here with no constant supply of energy, you say that it's still a soliton? Could you explain that?
We didn't
Maybe
hear soliton in the
Sorry,
reporting.
maybe I shouldn't have used this vocabulary and stay at your Earth model, but it is not the point of the discussion. I'm here to make the debate.
It's here,
And
like.
Okay, let's forget that word. And my question is, what is the different parameters that are important in your modelization of the propagation in the chain?
Okay, so there's a couple of important parameters, mainly the radius of the balls, the Young modulus, the Poisson ratio, as well the dissipative factor that is not, it's hard to, like actually it's not possible to be computed, like, or it's maybe possible but nobody yet done it, to compute in a theoretical manner, therefore it is measured. So those are 4 parameters that are very important in collision model. As well, there's another aspect as the initial velocity of the ball, which can influence the dissipation of energy. As I showed you, the higher I can show you even some of our slides. The higher is the velocity, initial velocity, the higher is the dissipative factor.
Okay,
Thank
thank you. I see you have understood the point. Maybe you have something to add.
Yeah, I have to speak about the physical meaning of dependence or upon important parameters of the experimental setup. You mentioned about dependence of speed of ejection ball upon the scale of the setup. Yeah. Did you explain, please, the physical meaning why it happens?
Yes,
and
of course. So we have two forces, two actually phenomena that are important here. This is the one, the gain of energy due to the magnetic interaction, and another phenomena which is the dissipative effect. So, I'm sorry. So therefore, those phenomena don't scale same way with the scale. As the higher the system is, the higher this dissipation, and it's not and the magnetic interaction doesn't scale so fast. Therefore, it gets more flat and flat.
Thank you
And
for your
thus-
answer. Maybe you have something to precise or add.
I want to precise where will be limit of increasing of the scale of the setup.
Okay, so I think that the balls we presented, like, let me move to one of the
And
slides.
also, I
Okay,
have
so
to-
here is the limit. I'm discussing the limit.
Mhm.
Okay, so you see that here we have the system of ours, which is 1 centimeter in diameter. This is the solution for the diameter of 16 centimeters. This is huge. So I think that at this point we lose the physical meaning for the assumptions of our model, as these collisions may no longer be described by Hertz collision theory. Higher order terms have to be included, and like it's pretty big. I see like there's no point in investigating further research because it's hard to make experiments on so large scales.
Yeah, and I want to precise, when we say that scale of the system increases, did you consider the relation between size of magnet and ball?
Yes, this was our research here.
Yeah.
We changed the length of the magnet, keeping its volume fixed,
Only length.
From now on, the team
and
members
the
can intervene.
radius of the balls.
Okay, so thank you. Maybe we have told a lot about the scale of the system. And here, actually, we have a question from Risha.
Please, could you explain from which parameters?
Yeah, maybe wait the microphone. Thank you.
Could you explain from which parameters of the system would the optimal number of ball depends upon?
Okay, it depends on the dissipation factor. In our case, where we took into account this effect showed us that the optimal value in theory is 3, and you can see also the plateau here, experimental. However, you having the theory behind it, we are strongly concerned that this is the actual maximum velocity. Also, when we have too high number of balls, more than one ball is separated, therefore those points land very near the axis and the velocity is much lower. So I think the great limit is due to the dissipation effects, as well and the increasement in velocity can be achieved using stronger magnets.
Okay, thank you. Maybe
Yes, yes, yes.
Risha
Could you
wants
call,
to-
please, another important properties of the system which can influence to final speed balls?
Okay, so I think that initial.
spite of-
Okay, so there's one more aspect, because I told you already about several important parameters, but there's one more that I still didn't mention. It is the initial squeeze of the balls. So as you have balls and there's magnetic interaction, they are initially squeezed. So we did. It is like it was not shown in the presentation. It was a lot of work and like some technical aspects, but the magnetic interaction also influences the dissipation between balls, as they are more or less squeezed. And if they are more squeezed, the dissipation is less.
And I have a question in this slide. Why why you didn't consider the more long
Okay, so as I
chain?
said, when we considered longer chains, they are not shown on the graph, as then more than one ball separates from the system, and this is why we did not present it here, and it limits the applicability of our model. Therefore, it's not compared here. If you have more balls, more than one ball separates. Therefore, the output velocity is much lower.
Okay,
this
thank you
limit-
both. I think we have talked a lot about this. Maybe one of the three teams are on other questions. Yes, here, Lyon, France.
Maybe we talked about mechanics, but there is also a huge understanding of magnetism that is involved here. And I would like to have the mind of the opponent about the origin of the magnetic force plotting. Do you think it's relevant to study the magnetic force considering the point of contact between the magnet and the ball? Would you have done differently? Could you please discuss it with the reporter, if I may?
So maybe first we can just show
Yes,
the
switch to
slide.
your graph of the magnetic
Of the
force as a
modeling
function of the
magnetic-
distance, please.
Yeah, yeah.
Okay.
And maybe you can start.
Yes.
Yeah. And I asked the reporter about approximation equation because, in my opinion, how Wright mentioned the reviewer, we can't apply in this case the dipole approximation. And I want to discuss with the reporter why we didn't, we don't.
So your statement is that we can or cannot apply. To make the things clear, do you think we can apply dipole approximation or not?
Yeah, I think that that we don't apply the dipole approximation, but I want to discuss it with you.
Okay,
1
so
minute.
What's your opinion
I
about
agree
it?
with you that we cannot apply dipole approximation, and this is why actually one of our first tries before we moved to numerical simulations, because it seems that if you would have a consistent theoretical model that included the use only some algebraic functions, it would be sufficient. However, this is the graph for the dipole approximation, and it is easily seen that the force is not does not resemble the theoretical curve.
30 seconds.
Moreover, I think that one may use this dipole approximation in order to compute the energy, because there are lots of fitting parameters here. However, the origin of this assumption is not fulfilled because it doesn't resemble the force. Therefore, I think it's not applicable here. And this was our motivation to investigate this phenomenon further using numerical simulations.
Okay,
agree
thank you
with
for your answer. Just maybe a last question.
No,
No,
I'm sorry, I don't
okay.
have time.
So thank you both for the discussion.
Thank you.
That
Thank
was
you.
very
Reporter, please conclude in 1 minute.
Okay, so I'd like to thank you, the opponent and the reviewer, for a great discussion. We could clarify several things. At this point, I would like to thank everyone involved in this program, especially our team who worked yesterday in Poland very hard to supply us additional data. As they were doing selective files, there was a lot of, there were several drawbacks mentioned to our presentation by the UK team. I would like to thank also the UK team for pointing out several drawbacks that we could improve on yesterday, and we could supply you with more data at the points that you really wanted us to have this data. And I would like to say that, yes, so, yes, thank you.
So we have questions from the jury. Erwan, Alice?
So I just want to ask a question to Poland about the dipole approximation, because it was pointed by Ernest Lyon. The point is, if you want to do a multiple approximation of the magnet, do you have to consider the distance from the center of the magnet or from the extremity of the magnet?
So if you want to compute a dipole approximation, there are surely several ways to do this. In our approach, we tried to do it the way that it is usually done at the center of the magnet. So the dipole was placed at the center of the magnet, and we investigate, because if you place it at
Yeah,
the
but
edge,
in
the
your
ball
graph
also has to have it on the edge, so their distance is 0. So how can you compute the force between dipoles when their distance is 0? You have to place it at the very center of the magnet. If you place it at the edge of the magnet and at the edge of the ball, the distance between those two dipoles is 0, so the force should be infinite. And I think it's not applicable. In our approximation, we place it at the very center, and the magnetic moment of this dipole was the density of the magnet.
Okay, but in your graph it was the distance from the edges.
The distance. Okay, so for
Okay,
calculating the distance
now it's another
force,
question.
we added the distance between, so.
I think I have more than 2 questions even. The first one is very short. On your plot, force versus distance, do you have error bars?
No. If you
Okay,
okay,
Then
so
the next one-
errors are within the points.
Okay, that's clear. Then the different thing for chain setup that you discussed so little. If you in the chain setup, if you take large balls first and small balls second.
Please.
Yeah, so in the chain setup, if you take large balls first and small balls second, you will get momentum transfer from large mass to small mass.
Yes,
Have you
but
considered this
the
kind
way
of
you want to
thought?
transfer the momentum is quite complex because at the very end you will have a large ball colliding with the small ball. So in this way the momentum is not transferred directly, but it is at the angle, and there has some of the energy is not transferred in the line,
True, you
but
could-
also to the bottom.
You could adjust the, but okay.
I could adjust the.
Then maybe the last and the longest question. So you were using the Hertz classical theory of collisions, and when Hertz published his theory, it was heavily criticized for one thing, and this was surface effects. So because it doesn't take anything that happens on the surface. So when you were working with the balls, you probably touched them with your fingers, and fingers are sweaty. Did you clean up the surface of the balls?
Okay, so maybe I will address this question differently. We always touch them with the same hands. So we always touch it with the same hands. So if there was any dirt, it was always the same. And if there were some effects there, so if we would once clean them very, very precisely, the effect should change in precise when it's a bit dirt on it. But if we have a dirt, I think that, and we also measure this dissipation factor without cleaning the balls, making them purely clear. So I think those effects are firstly measured in our in the between measurements, and if this they may average so that the result is correct.
Okay. Okay. I have two small questions. First one, could you please turn on to the graph where you had eject velocity, impact velocity? And the question is that the plot looks rather clear for me, but it's just like a quadratic dependence. Did you try to estimate it with some kind of energy estimation law?
Okay, so this at the beginning looks like a quadratic dependence, but if you will look further on it, and I have a graph here, it's no more than linear.
Some quadratic dependence
So
with
here
losses.
it's a quadratic dependence, and then it's not. So at the very beginning, when we have small ejection velocities, we did not try that. Maybe it's a good approach. However, like it is.
Okay, the answer is clear. Then please to the experimental setup that you use it. You have a picture of it.
Yes.
Did you try to estimate the ratio of the rotational energy to the kinetic energy?
So what we did, we did not estimate that factor exactly. However, we measured the velocity using this setup, and this setup was checked to be correct using high-speed video measurements, where we have a ball, we track the ball, we determine its velocity exactly from the video. However, this is a long analysis. Therefore, we wanted some tool to be a better one with that could result faster and not use advanced equipment. Therefore, we checked if the velocity measured by this system and using high-speed measurement is the same. Therefore, I conclude that the rotational energy is small in comparison to what we measure near to this setup. After some distance, this rotational energy may influence, and yes, it's like the energy would partition between rotational energy and translational energy for there to be no sleeping on the surface.
Just one question. Could you play with the permeability of the balls? For instance, the incoming balls could have a different permeability than the outgoing balls, and this might change the final velocity.
Okay, so are you referring to the hysteresis or the initial magnetization or the material properties?
Material properties.
Okay, so our balls were supplied by NPA Scavina, who supplies steel for industrial application, and this is high quality steel, and all of the balls are with industrial precision have the same properties.
Yeah, but if they do not have the same properties, then you may.
Yes, if they have different properties, this effect may be changed, as the force of magnetic interaction at the beginning would be, for example, greater than at the end, and this could increase the outlet velocity.
Last question. Yves Bréchet.
Yes, I
would like you to make clear for me what are the relative magnitude of the various energy terms, in terms of stored energy, which is released, in terms of dissipated energy.
Okay,
Let me finish.
So-
So you have the kinetic energy, you have the magnetic energy, you have the plastic energy, the plastic dissipation. You have of course the elastic energy stored in the balls. I mean, what are the relative magnitude of all these quantities?
Okay, so the energy stored in magnetic field at the beginning, if you have a ball and there's a magnet here, so the difference in potential energy is 30 millijoules. This allows this ball to travel at the speed of 1.7 meters per second. This system would travel there's other way with speed of 0.3 meters per second. And during this collision phase, when we have three balls after the setup, there's energy dissipation of 24%. So this energy, 30 meters per second, is 30 millijoules, is lost to be about like 3/3 of this. So it's like, okay, so let's say 30 times 3 by 4 millijoules at the end. And then the velocity of ejected ball can be, depending on the parameters, 1.45 meters per second.
Where does the dissipation come from?
Okay,
dominantly?
so you have the dissipation because material is deformed, and there's internal motion of particles. Like when you deform the material, the energy also dissipates. Like if you have a blade, then you make it vibrate. After some time, it loses its vibration. Some to the area resistance, but also due to the internal strains and stress. When you move, the molecules move between each other, and this causes energy to dissipate into heat.
Okay, but I'm sorry, we're running out of time.
I will ask for your email.
Thank you very much. So, thank you. One question?
1 minute. I suggest that for the future discussion, we have only one question per member of the jury. Otherwise, not everybody can speak. Please.
It's a big jury. So, jury, please put up your marks for the reporter, the opponent, and the reviewer. Thank you. And jury, please cut your phones because it's doing the microphone some fuzzy interferences. Thank you. Maybe keep it. Oh, no worry. Mettez les micros là et puis on vous donnera un micro. Jury, is it okay? All the juries are ready? Okay. So, Vladimir, is it okay? Okay. So, juries, please show us your mark for the reporter team, the Poland. So we have 8, 9, 9, 9, 8, 7, 7, 7, and 7. Thank you. Jury, please show us your mark for the opponent team, team of Russia. We have 2, 3, 3, 3, 5, 5, 6, 7, and 6. Thank you. Jury, please show us your mark for the reviewer team, team of France, INS Lyon. We have 5, 6, 7, 7, 8, 7, 6, 6, and 7. So now we have 4 minutes time for remarks of the jury. Please stay short in order for...
Sure. Who would like to explain? You want to explain your grade?
First of all, to the reporter, I have put relatively low mark. If it was on the tour, I would put 9 or 10 without hesitation. Now I was trying to calibrate, and first of all, the main important thing that you didn't do, you didn't consider all the limiting effects for increasing velocity. And by that I mean the ball can break. That's one limiting effect. You can crack the surface, you can break the ball. Another one is like you can consider all these cannon chains. That one was not considered, and I think actually surface effects are important there, they were not accounted.
Thank you. Sébastien? Georgia. No, Georgia.
Okay, so my main point is that all of you in the discussion missed that you had to fix the magnet. It's like super important. This maximizes the speed. This is not making your problem better. This is the solution to the problem, because your limiting factor when you do not fix the cannon is the mass of the cannon. You add balls, has more mass, more momentum goes to that and not to the final ball. It's not the magnetic energy that limits your system.
Okay, I have put some extreme marks, for example, lowest mark for a reporter and lowest mark to the one of lowest mark to the reviewer, and I was just to comment my marks. Firstly, for the reporter, I think you have done good work, good experimental work, but you didn't investigate it in rather deep physics enough. It means that, as opponent said, and it's why I have improved his mark, that you should consider many stages. For example, you have a plot ejected speed, impact speed, and it can be easily, I think, approximated with some kind of energy conservation law, but with losses. You have some energy from ejected speed, and you just add this energy and to the difference of energies, of potential energies, and have some losses, and you will obtain a good theoretical model for this one, and you can easily consider many stages interaction. And when you scale you up, I would correct Dmitro that not the ball will break, the magnet will break, I think, because ball.
Okay.
Yes, and about the reviewer. Okay, the reviewer, I think, has done good work, but solitron propagation model was really bad. I think you should point out more important physical questions here. For example, the many stages, the magnet pole interaction as it was done by opponent, but you have challenged the discussion to not the best one, as I think.
Thank
okay.
you. I think we have a remark from Sébastien Balibar.
Maybe, I don't know. Anyway, I found the reporter, sorry, the reporter really brilliant. They have done a lot of work. You have not considered everything, of course, but that's impossible, both in the preparation during a few months and in the presentation today in a few minutes. So for the time allowed and so on, I found it beautiful, and I give you 9. The opponent, I was a bit disappointed because you spent where is he? I don't know. You spent half of your time with very general considerations. It took you a long time to arrive to some questions which were not extremely clear. So I'm sorry, I was a bit disappointed. I didn't see in your comment, in your criticism, anything which would help improving the solution, or you know. As for the reviewer, this is a difficult role because but they managed the discussion quite well. I think they had a few questions. They were fair with everybody. They were not brilliant because it's very difficult to be brilliant when you are a reviewer. It's easier when you are the reporter. So that explains why I give them a good note, but not an excellent note because of their unfortunate position as a reviewer. Somebody else?
Okay. Yves Bréchet.
I would agree with all what Sébastien said, but I would add to the reporter, which I really enjoyed, that you might have neglected things, but you have not forgotten them, and I think that's very good.
Okay, thank you very much to all of you.